Good morning. I'm Jin Gao from Tongji University. It's a really great honor for me to host this keynote speech. Today we will have a very distinguished professor from the University of New South Wales, Australia, Professor Mattheos Santamouris. He's the editor-in-chief of one of the Energy and Buildings Journal, and he's also editor and author of 20 international books published by Elsevier, Earthscan, Springer. He is ranked as the top world cited researcher in the field of building and construction by the Stanford University ranking system for 2019 to 2022. He is also a highly cited researcher in the Clarivate ranking for 4 continuous years. Today, the title of the speech is Regional and Global Overheating and its Impact on Human Beings. Let's give a warm welcome to Professor Santamouris, please.
Good morning. Thank you so much for the invitation. Is there a serious problem of urban overheating around the world? Yes. Actually, we have, let's say, more than 13,000 overheated cities around the world. There are more, let's say, than 1.7 billion people which lives under very severe overheating conditions. Since '98, the number of overheating hours around the world has increased by a factor of 3. Is there any serious impact regarding, let's say, the overheating? Yes. Overheating is increasing the energy consumption for cooling. At the same time, is increasing very much the peak electricity demand, in the building sector. Also, it has a tremendous impact on heat-related mortality and morbidity. It decreases the human, let's say, productivity and affects very much the survivability level of low-income households. Do we have enough evidence? Do we have proofs about, let's say, the amplitude of urban overheating and also about, let's say, the real impact of, let's say, high temperatures in our cities? Yes. For example, regarding the energy consumption, we know actually that the total penalty that we are paying because of, let's say, the higher temperatures around the world is close, to, let's say, 237 kilowatt hours per person, or plus minus 130. So every one of us, because in average, because of the overheating, let's say, of cities, is paying an additional penalty of close to 237 kilowatt hours. At the same time, we know that because of the higher temperature, the efficiency of thermal and nuclear power plants is decreasing really considerably. For each degree of temperature increase, the efficiency of the power plants is decreasing by about 0.6%. So imagine that during a heat wave, with 10 degrees of temperature increase, the decrease of the efficiency of power plants may be of the order of magnitude of 6 or 7%, which is really very important. At the same time, it increases tremendously the peak electricity demand and obliges utilities to build additional power plants. This has a tremendous impact, on the cost of electricity, and also these power plants operate just for a few hours per year. Is it, let's say, so important, the so-called regional climatic change, or the global climatic change is more important, than the urban overheating? If we try, for example, to present an example, which is the magnitude of the change, I'd like to show you what has happened, for example, in the city I'm living, in Sydney. In the 90s, the number of cooling degree hours, in a coastal area, not very much affected by urban overheating, was 820. In, let's say, 2023, in the same area, the number of cooling degree hours has increased by a factor of 33%. Yeah. this is the impact of the global climate. But once we move inside the city, towards the western part of the city, where urban heat island and urban overheating is important, in this case, the number of urban, let's say, the number of cooling degree hours has increased by a factor of 81%. And if we move to the very western part of the city, where really overheating is very important, the number of cooling degree hours has increased by 300%. And these are real numbers. So you understand that the impact of regional climatic change is very important in our cities, much more important than the impact of the global climatic change. Is it just the impact of urban overheating on energy that really has to worry about it? No. The environmental impact of urban overheating is extremely important. We know very well that because of the high temperatures, we have photochemical reactions in the atmosphere, and this increases the concentration of the ground level ozone. Ground level ozone is a killer. And actually about, let's say, 87% of the episodes of high ozone level is because of the global and regional overheating. So the impact really of high temperatures on the environmental quality is extremely high. But it's not just that. We know very well that during the period of heat waves, or when temperature is increasing, the emission from power plants is increasing tremendously. Average statistics shows that about, let's say, the increase of the emissions by power plants because of the temperature increase is of the order of magnitude of 3%, per degree. So imagine during a heat wave that you may have 10 degrees of higher temperature, the increase of the emissions of SO2 or NOx or CO2 may be of the order of magnitude of 35%. This is really very important. At the same time, as I have already mentioned you, urban overheating has a very serious impact on the peak electricity demand. If really you try to see and examine the number of, let's say, electrical grid failures recently in the United States between, let's say, 2015 to 2021, you will see that there is a tremendous increase during the very last years that affect very much the efficiency of the power plants and affects also the cost because it asks for additional, let's say, investments really to counterbalance the impact of the very high temperatures. Unfortunately, the impact on energy and the impact on the environment is, of course, important, but is not the most important of the impacts of urban overheating. Actually, urban overheating affects very much low-income population. Low-income population is living in houses where really the environmental conditions or the thermal conditions are not really the most appropriate. No insulation, no double glazing, perhaps no shading. As a matter of fact, because of the low quality of the housing, indoor temperatures may be extremely high. And we have enough, let's say, proofs and enough evidence that people is living really under extreme indoor conditions because of the overheating. Do we have enough evidence about this? Yes. A very recent study performed, in Los Angeles, in the United States, has shown that there is almost a linear relation between the ground temperature and the income of people. People which really is of low income is living in areas with very high surface temperature, which means no vegetation. So people really of low income is living in areas which present a very high, let's say, ground temperature. But we have more evidence about this. And another study has shown really the important discrimination between, let's say, the area that we live and the income. For example, this study that was performed in the United States showed the relation between income of different, let's say, groups of people against, the temperature, against urban heat islands, urban overheating. And you may see, for example, that white people is living, the blue one, in areas of much lower temperature, while people, of lower income or ethnic groups, they are living in areas with much, much higher, let's say, temperature. Is it enough? No. We have performed a lot of measurements in low-income houses during the very last years, and I'd like to show you some of the measurements, for example. In Greece, during a heat wave, while at the beginning of the heat wave, a study that was performed in about 400 let's say, low-income houses, showed that while the temperature at the beginning was close, let's say, to 25, 26 degrees, excellent, after 5 days of, let's say, heat wave, temperature, average indoor temperature was close to 35 degrees, and we had, let's say, more than 50% of the buildings with indoor temperatures more than 40 degrees. The same in Sydney. Temperatures not during a heat wave, maybe during summer, more than 40 degrees. And at the same time, the concentration of CO2, because they close windows, they close the doors, they close everything, maybe, let's say, 3 to 4 times higher than the threshold. So because of the overheating, people, low-income people, is living really under non-acceptable indoor conditions, and this is a problem. And this brings us to the serious problem of overheating, the problem of health. The problem of health is not a linear relation with temperature. It depends very much on several parameters, and especially on demographic parameters, socioeconomic parameters, and the health infrastructure in the area. In average, we know that actually people is living in the more, let's say, warm areas of cities. They have 6% higher risk to, let's say, die because of or compared to those that are living in the coolest part of the city. 6% higher risk, really, of heat-related mortality. Sorry. At the same time, there is a lot of work that has been done during the very last years trying to understand the impact of overheating on, let's say, heat-related mortality. Is it just the outdoor temperature that affects the, let's say, the magnitude of heat-related mortality? No. We know that while, let's say, the impact of the outdoor temperature on heat-related mortality is close to 6.1 deaths per million because of the high temperature, when this is combined with higher indoor temperature, this is increased to 23.5, let's say, deaths per year. So this means that the combination of high outdoor temperatures together combined with, let's say, high indoor temperatures really is a very serious problem that may, let's say, kill a lot of people. You may expect that because of, let's say, the high temperatures, heat-related mortality has increased during the last years. No. Heat-related mortality has decreased during the last years. If you really check the statistics, if you check the statistics, you will see that in most of the cities, during the last years, the relation between, let's say, mortality, heat-related mortality, and temperature is negative. Why? Because we are adapted. And this is not a physiological adaptation. This is an engineering adaptation. We have more air conditioning. We have better buildings. So this is what is happening. Unfortunately, this trend seems to reverse during the very last period because of the very high temperatures. And the actual, let's say, predictions from Lancet and the group of experts shows that for most of the areas, and especially in the Southeast Asia, the, let's say, expected increase of the heat-related mortality is really tremendous. And there is a decrease of, let's say, cool-related mortality or cold-related mortality. Are we sure about this result? No. We are not sure. Why? Because there is a lot of uncertainty about these issues. And this uncertainty is coming because of several parameters. Climatic model. We are predicting, the future using climatic models. In most, let's say, of the studies, we are using the more extreme scenario. But we're not sure about it. Second, the mortality model. We have established association between temperature and mortality rate. This association is based on past data. This past data will really be valid in the future? No, because we don't know how much really we will apply. And adaptation is very important. And adaptation is not only physiological, it's engineering. So we're not sure about the adaptation. And also we're not sure about the future population. So when really we try to be serious about the prediction of the future, let's say, mortality as a function of temperature, we may have a tremendous, let's say, uncertainty, and you see some results from a recent study. We may have a tremendous increase of mortality if we are not adapted, if climatic change is serious, if the population is increasing a lot, or we may have a small decrease of mortality if really we treat the whole thing in the proper way. So while the problem and the association between temperatures and, let's say, heat-related mortality is very serious, there is a very serious uncertainty about this issue. But it's not just mortality that is affected by temperature. It affects very much human health, and especially, you know, the, let's say, problems, psychological problems, and mental health of human beings. We know, for example, very well that there is a tremendous increase of, let's say, assaults and murders as a function of temperature. The higher the temperature, the higher, let's say, the aggressivity. At the same time, there is a very interesting study that was published quite recently that counted and really evaluated the number of, let's say, aggressive tweets as a function of temperature. And you can see, for example, in this graph, that the higher the temperature, the higher, let's say, the aggressivity in Twitter. So this affects very much, let's say, the whole mental health of people. Is it just energy, environment, health, low-income people that is affected by, let's say, higher temperature? No. Human productivity is extremely affected by, let's say, higher temperature. Recent studies have really evaluated, using millions of people, that when temperature is increasing above 30 degrees, human, let's say, productivity may decrease by 60 or 70%. This is tremendous. Recent report published a month ago, during the heat wave in India, in Delhi, where outdoor temperature was close to 50 degrees for about 4 or 5 days, shown that productivity in Delhi has decreased by 90%. You understand the economic impact, you know, of this thing? This is what has happened actually. What do we expect for the future? Unfortunately, actually, there is a shortfall of about 330 million homes in the world. And we expect that during the next years that this, let's say, shortfall will increase by 440 million, let's say, homes. At the same time, the additional, let's say, housing needs will grow by more than 77 billion square meters of floor space, which is almost, you know, the total floor area or the total area of China. You understand that we need tremendous, let's say, new areas for housing because of, let's say, the overpopulation and the needs, you know, for proper housing. And most, you know, of these new developments will happen in, let's say, in developing countries, India, Indonesia, Brazil, etc. In brief, and this is very important, we build 1 Paris per week. This is the rate of new construction. 1 Paris per week. What does it mean, this tremendous increase of construction activities? It means that something will change in our cities. Not because only of the overpopulation, of the regional and global climatic change, but also of the human activities. All models we have shows that by 2050, the temperature of the cities during the night period may increase up to 5 or 6 degrees. It's not the same everywhere in the world, but this is the average. In some places, the night temperature may increase up to 7 degrees. The daytime temperature may increase by 3 or 4 degrees. All models agree that in the future, our cities will be much more warm. Which is the energy impact of such a development? Cooling. We have a tremendous increase in penetration of the air conditioning in the world. Using different models, different studies have shown that by 2050, the energy consumption of cooling in the world may increase between 1,620% up to 2,270%. Do you understand this? The energy impact, the economic impact, the environmental impact, the emissions impact, the, let's say, financial impact. Just one city of India, Mumbai, may present higher electricity consumption than the whole United States by 2050 because of the air conditioning. And the cost, of course, of this overheating is tremendous. It is actually 500 to 700 billion American dollars per year. This is the cost of the overheating. And it is expected that it will increase up to 1.3 trillion American dollars by 2050. So the cost of inactivity regarding urban overheating is tremendous, actually. But it's not just the energy problem. It is the social problem which is associated with the energy problem. If really we see and we examine the penetration of air conditioning in 4, let's say, developing countries, Brazil, Mexico, India, and Indonesia, as a function of the income of the population, you will see that there's a tremendous penetration in high-income population and a small, let's say, penetration in the low-income population. So by 2040, it is expected that about 1 million households just in these 4 countries will not have, let's say, proper air conditioning and will live at temperatures higher than 40 or 45 degrees the whole year. And of course, this has a tremendous impact, of course, on the energy consumption. So the social stratification, which is, let's say, generated because of the overheating and the consequent financial, let's say, development will be, let's say, very important, especially, for the low-income population. So we have condemned a huge part of our population, of the world, because, of the overheating, because of the non-financial development, and because of the many other things. These are the bad news. Sorry about the bad news. Do we have really good news? Yes, we have good news. During the last, let's say, 15, 20 years, there's a very important research that has been carried out regarding, let's say, mitigation. We have developed techniques, we have developed technologies that can decrease the temperature of the cities. Of course, I don't have the time to go through all the technologies, but I'd like to show you some developments that, let's say, has happened in our lab, trying really to decrease the temperature of cities. One of the major developments that has been achieved during the, let's say, the last 5, 6 years is the development of the so-called photonic materials for buildings. Materials that present a very high reflectance to solar radiation, more than 95, 96, 97%, but at the same time, a very high emissivity in the atmospheric window. So these materials may, let's say, reject the excess heat directly to the space through the atmospheric window. So these materials that has been developed, and I will show you some of this development, for example, for example, the development of the first generation materials that we had in Sydney, which, let's say, were composed by, let's say, 2 layers, a reflector that really reflects the solar radiation, and at the same time, a material which is optimized in order to emit in the atmospheric window. These materials that have been developed and have been tested in the Australian desert present during the day, under the sun, under the Australian, let's say, desert, subambient temperatures up to 9 degrees. It's a natural air conditioning. For example, why? The ambient temperature under 1,000 watt was 35 degrees. The temperature of the materials was 26, 27, 28. So it's a natural air condition that when used, in cities, may, let's say, decrease the temperature. Is it simple really to apply these materials? This was the first generation of materials. During the very last period, we have developed much simpler, let's say, materials. One material that was developed together with UCL in London, it is a new paint that we have developed, which is composed by 2 materials. Let's say PDMC, and at the same time, polyethylene. So we have created a new paint that really can be easily applied in any surface. And when really tested this material, it presented under the sun and, in the Australian desert, up to 3 degrees lower surface temperature than the ambient one. So we have really materials now that present very high efficiency and may decrease the temperature of our cities. However, there are important problems associated with this kind of materials. First, we have very high reflectance, 98%. You can't use these materials on pavements, on facades. Very reflective. Second, these materials are really white. We cannot have white surfaces everywhere. Third, there's an aesthetic problem. And third, if you like, the problem is that when these materials are used in temperate climates, increase, the heating energy demand. So we have seen that really we need to modulate the optical properties of the materials, because these materials may offer, a tremendous cooling potential, but may, let's say, present some problems during, let's say, the winter period. But once really we are able to modulate the reflectance, so the materials present high reflectance during the summer and low reflectance during the winter, and at the same time modulate the emissivity, have a high emissivity during the summer, a low emissivity during the winter, or both of them, we may have win-win conditions. Decrease the temperature during the summer, increase the temperature during the winter. Smart materials. How this can be done? How really it is possible to decrease the reflectance and at the same time keep the same low temperature? What we have done is that we're using, together with photonic materials, fluorescent materials. These fluorescent materials absorb, in low wavelength up to 450, but emit immediately, almost 90% of the absorbed solar radiation in other wavelengths. So in this case, we may, let's say, have color materials which present a low reflectance, but at the same time may have an additional cooling, let's say, mechanism. We have prepared these materials by using a combination of photonic and fluorescent, let's say, techniques. I don't really have the time to go to give you more, let's say, details. But I'd like to show you, let's say, these materials and also show you the results. This is the comparison under the Australian desert of the color, let's say, yellow photonic fluorescent materials against, the white materials, the white photonic materials. You can see that by adding color in these materials and also fluorescence, we have exactly the same temperatures. So we can have color materials which present, very low temperature, similar temperature, like, let's say, the photonic materials. However, what is really amazing is that these materials, the color materials, present almost 4 degrees lower surface temperature than the white materials, the conventional white materials. So now, for cities, we may have color materials for facades, for pavements, for roofs, where really we may have, let's say, very low surface temperature, which really may contribute to, let's say, mitigate urban heat. And these materials may, let's say, present up to, let's say, 0.2 or 0.3 or 0.4 degrees higher temperature than the very advanced photonic materials. So these are very, let's say, materials of very high, let's say, potential. In conclusion, the recent developments we have on mitigation technologies has allowed us from a potential 10 years ago to decrease the temperature of cities close to 0.5 degrees, now to decrease the temperature of cities up to 2.53 degrees. We have more than 250 cities where temperature has been increased by 2.5 degrees. Actually, the development, of the photonic and the fluorescent materials has allowed us to decrease the temperature of cities up to 4.55 degrees. We have the chance to coordinate the biggest mitigation project in the world in Riyadh, in Saudi Arabia. By using these technologies, advanced technologies, we have calculated that we can decrease the peak temperature of the city up to 4.5 degrees. In collaboration with LBNL, that's in Hong, we have calculated the energy impact of about 3,323 buildings downtown the city. And we found that it is possible to decrease the energy consumption of this building in Riyadh by 35% by using this mitigation technology. The study has been finished, and now we implement this project. In about 3 years, we will know the exact results. At the same time, similar studies in Sydney have shown that by using these techniques, it is possible to decrease the energy consumption in the city up to 29% when the materials, are considered at the, let's say, building scale, but when we consider at the same time a large implementation at the city scale and at the building scale, the energy consumption for cooling may decrease up to 49%. So there is really hope. What is also very important is that actually the use of these materials in low-income houses may decrease indoor temperature up to, let's say, 9 or 10 degrees. And this is not a computer simulation. These are real results that we have obtained through, let's say, monitor. Also, calculations performed all around the world have shown that when really these mitigation technologies are used, we may decrease heat-related mortality up to 19.8% per, let's say, degree of temperature drop. So there is a win-win situation that really decreases temperature, decreases energy consumption, decreases really heat-related mortality. Similar results are obtained also for additional greenery. Conclusion. We have the technology to decrease the temperature of cities. We know the impact. The question is why we don't really implement it. Because those that they govern us, they really understand the whole issue by using financial, let's say, terms. So most, of our leaders, they like to monetize the cost, really, of overheating. And as I mentioned to you before, the cost of the overheating actually is, the cost of overheating actually is close to 500 billion per year and will increase up to, let's say, 1.3 trillion by 2050. So who is paying this cost? Taxpayers? Why this has to be distributed between all the taxpayers? Are we responsible for what is happening? No. In order to solve this problem, we need to develop financial mechanisms in order really to find the proper, let's say, resources to finance proper mitigation technologies. It is impossible really with the actual budget we have in cities and the budget which is spent by the states to, let's say, finance mitigation technologies. The actual cost of, let's say, decarbonization is close to 1.6 trillion per year from now to since 2050, and this money do not exist. So in order really to finance this specific, let's say, effort, we need really to push the financial sector to enter the game. But this can be done. This can be done by creating a new market, a market that really will first take care about the quality of building spaces, etc., technological problems, but at the same time will put a value on the urban mitigation and adaptation capital. Those that they really increase the temperature in cities, they have to pay. Those that they increase really the temperature in our urban environment, they have to pay. And those that they decrease the temperature in our cities, they should really benefit from the credits. So we have to create a new market. So those that really, they don't care about what is happening in the environment, they don't care about the overheating of cities, that they build new buildings without really taking care of the overheating. Those that they use whatever materials, black asphalt everywhere, those that they don't really consider the anthropogenic heat, they have to pay the cost of overheating. And those that they take care and they build, low temperature, low energy, let's say new developments, they need really to have the credits for it. So by creating such, a market, we may, let's say, boost the whole mitigation technologies in the world. How this can be done? Unfortunately, the building sector It's very much fragmented. Technologists, energy experts, they do their research. Epidemiologists, they do their research. Energy people is doing, let's say, it's research. Economists, they do the same. So we're fragmented. And we don't have, let's say, a good communication. So the whole, let's say, effort actually in our cities is not holistic, is not integrated. If really we wish to face the problem of global climatic change and local climatic change, we need really to integrate our effort and have, an holistic approach. And this is my last slide. What really happens around the world? We know very well that we have a serious problem of overheating. This is extremely well documented. We know at the same time that there is a very important scientific knowledge about mitigation. We know that we can decrease the temperature of cities. We know that we have the technology. However, most of the implemented mitigation strategies are based on empirical knowledge. Let's plant trees somewhere, let's change something somewhere, not scientific knowledge. Empirical knowledge that do not really contribute to decrease the temperature of the city. We know very well that politicians and those that they really take decision makers, they like very much simple solutions. For example, just planting trees. But this may have an impact, but is not really a scientific approach that may decrease the temperature. So the lack of the proper policy in our, let's say, cities is increasing and aggravating the problem. Temperature in cities is increasing almost everywhere around the world. How to face the problem? First, we have to understand that this is a multidisciplinary problem. It's not just a technological problem. It's not just a medical problem. It's not just a financial problem. It's an holistic, integrated problem. And we need really to act in a combined way. And the last and the most important, if we don't really fix it, if we don't really proper measure, the impact on energy, on environmental quality, on low-income population, on mortality, on health, etc., will be really tremendous in the future. So what we need really to do is first to design integrated and holistic mitigation policies which are based on scientific knowledge, because there is scientific knowledge and not just on empirical approaches. Thank you so much.
Thank you so much to Professor Santamouris. So we have more than 5 minutes left. And Professor Santamouris explained how the overheating or urban heating impact our human beings, how it impact our economics, society, energy, and also our health, and also give us some solutions to mitigate the heat. And maybe we can also establish some overheating market to counterbalance the urban heat and other solutions. Maybe we also need to rethinking how we should do and how we can do in the future. Thank you very much for your impressive presentation. So maybe we can have several questions for the wonderful presentation. Yes.
Thank you, Professor. That was a really interesting and eye-opening presentation. I'm just concerned about the materials that you were mentioning. They do serve their purposes, but I just want to know, how have you considered the environmental impact or the embodied energy of those materials?
The embodied energy of these materials is, let's say, maybe much lower than the embodied energy of conventional materials, But materials will be used all the time, in the built environment, So the potential increase of the embodied energy of, let's say, alternative technologies is much, much lower than the decrease, of the energy that may, let's say, create. So embodied energy is very important, but it's not the major issue. It's not the major issue. The major issue is overheating and the increase of the temperature and the consequent, increase of the energy consumption.
Okay. Thank you.
Thank you very much, Professor Matt, for a great presentation. So I have two questions. So first is that you mentioned that in a poorly designed city, the overheating can goes up more than 300%, and this is very eye-opening. Could you please elaborate a little bit more about this? So what mechanism of this? Is that the concentration of the heat because of the poor urban ventilation or something? And also, could you please elaborate a little bit more about the features of the poor designed cities? Because that's something we are really curious, because in a city, sometimes people will think that they all look very, very similar, but in your presentation you showed that in a poorly designed city and a well-designed city, the overheating can be really, really diverse. What do you think is the key features of the poor designed city that cause such devastating overheating? Thank you.
I'm not sure if I have understood completely, your question. Actually, in the reasons of overheating, let's say in cities, first of all, the very high absorption of solar radiation by the structures, and building, pavements, whatever it is there, because we are not using the proper materials. Second, anthropogenic heat, which is, let's say, very important. At the same time, phenomena which has to do with, let's say, the lack of ventilation in the city, and also, let's say, greenhouse effect that does not allow the, let's say, infrared radiation to escape. So these are the reasons, as I mentioned at the very beginning, the overheating, let's say, period in most of the cities, almost all cities, has increased by a factor of 3 during this period. So the problem of overheating of our cities is a real problem, really problem. And it's extremely well documented at the same time and is increasing continuously. On the other hand, all, let's say, simulations we have for 2040, 2050 shows that, in the future, let's say in cities, the temperature increase, during the nighttime will be very important. Not so much, let's say, the maximum temperature, but the minimum temperature, the nighttime temperature. 6-7 degrees, this may have a tremendous impact on the energy balance of cities. Why? Because buildings will not, and the structure will not be, let's say, cooled during the night period. So the temperature will be accumulated. At the same time, most, of the passive cooling techniques we're using, night ventilation, etc., will be very much affected. Third, and this is very serious, because of the very high, let's say, temperatures during the night, the peak electricity demand is transferred during the night. And this happens now in Europe. What does it mean that? It means that during the night, we don't have photovoltaics. So in this case, and especially during heat waves, we don't have also wind speed. We don't have wind energy. Because during, let's say, heat waves, the wind speed is very low. So during, the extreme phenomena, you don't have renewables, or you have very low renewables. In this case, either you need to have a very high, let's say, storage capacity, which means a lot of money, huge infrastructure, and huge cost, or you need to operate, conventional energy sources. So this is a serious problem that increased tremendously the cost of energy provision, in cities. This is the main problem that we are facing today.
Thank you so much.
Okay, maybe one more question.
Thank you very much. Hey, Matt, very impressive presentation. You have one interesting slide, talk about charge tax for heat emission from the building. So what about those heat emitted from the AC, air conditioning systems? How do you charge tax for those heat?
Can you repeat your question? I'm sorry.
Okay, you have a slide. You have a slide showing like building emitting a lot of heat. You talk about probably taking penalties for those heats, right? So we have a lot, like Shanghai, for example, we have a building using a lot of AC, and then the AC also dumping a lot of heat to the urban area. How do we charge tax for those heats?
I'm not saying tax. I have not proposed taxes. I have proposed
You have one slide showing like we should like.
credits. Yeah. I will explain you.
Okay.
This system, applies already for the decarbonization all around the world. You have the carbon taxes and you have the carbon credits. You have ESG. For example, all companies that really they produce, let's say, a lot of CO2, they have to buy, let's say, carbon credits. And what they are doing is that they are going to Indonesia or to India, I don't know where, in Amazon, and they plant trees. And I'm not sure if such, a carbon credit has any impact on the environment. Because first, you will get, the result in 20 years, and you're not sure if really, after 20 years, the forest will be there. So there is a serious problem, actually. So what I'm proposing is to transfer this mechanism, financial mechanism, of, let's say, that applies on the decarbonization, on urban overheating, for example. In new cities around the world, you have new developments, new settlements. They don't care at all about overheating. They just build the very conventional way. They increase the temperature in the area, and this impact, financial impact, is paid by the taxpayers. On the other hand, you have the possibility, because the technology is available, to build and decrease the energy consumption, the carbon emissions, and at the same time, decrease, the potential overheating, mitigate. So, shall we really treat the same way both developers? No. Those, they don't care. They need to pay the cost. And those they care, they need to have benefits. How this can be done? This is another discussion. I can explain you how. We can easily, let's say, count the sensible heat which is emitted by, let's say, a structure. So by counting the sensible heat, we can have fines and carbon credits or overheating credits. This is the system that is going to be applied, since next year in Europe, in the 100 zero carbon cities. So I think that if we don't really impose specific measures to those that they don't care in the built environment, we will not succeed really to improve the quality of our cities. If we allow those and we permit to those that they don't care about the quality of the urban environment to continue building this way, we will have, let's say, cities by 2050 which will present, temperatures up to 5-6 degrees. And in this case, the reactive measures will cost 10 times higher than the proactive measures that are really proposed now.
Thank you. We can talk more afterwards. Thank you.
And thanks all your participating, and we have a gift for your great contribution. Oh, it's coffee break. Thank you for your participating.